Hello students. So in the previous video we took some properties of Z transforms. Now we'll continue in this video. We'll continue with the properties of Z transform, that is the remaining ones, and we'll take some examples on that. Okay. So the next property is convolution property. So the statement says if x of n gives x of z with ROC R1 and y of n gives y of z with ROC R2, then x of n convolved with y of n give x of z into y of z with R1 intersecting R2. So this is the statement. So convolution in time domain is equal to multiplication in frequency domain. So to start with, we'll start with the term Z transform of x of n convolved with, okay, first one, Z transform of x of n is equal to summation n varying from minus infinity to plus infinity x of n z to the power of minus n. Call this as 1. So Z transform of x of n convolved with y of n is equal to summation x of n convolved with y of n z to the power of minus n. If you elaborate this, so we'll get from the definition of convolution sum, so you can write it as summation k is equal to minus infinity to plus infinity x of k y of n minus k z to the power of minus n. So interchanging the summations. Now we interchange this to summation here. Summation k is equal to minus infinity to plus infinity x of k, summation n is equal to minus infinity to plus infinity y of n minus k z to the power of minus n. So this can put in the bracket this term. Now this, in this term, let's replace this n minus k with some other alphabet. So put n minus k is equal to L, that gives n is equal to L plus k. So summation k is equal to minus infinity to plus infinity x of k, and here summation, this n will change from L is equal to minus infinity to plus infinity. N minus k is replaced by L here, and z to the power of minus n is replaced by z to the power of L plus k. Now continuing that, k is equal to minus infinity to plus infinity x of k, L equals minus infinity to plus infinity y of L z to the power of minus L into z to the power of minus k. Now this L stays here, and this z power minus k will become the constant with respect to this limit. So taking that outside, so k is equal to minus infinity to plus infinity x of k z to the power of minus k into L is equal to minus infinity to plus infinity y of L z to the power of minus L. Now these two, if you compare with equation 1, so this is nothing but x of z, and that is y of z. And here we started with z transform of x of n convolved with y of n. So hence the proof for a convolution property. So next is differentiation. So it says if x of n gives x of z with ROC R, then n into x of n will give minus z differentiation of x of z with respect to z with ROC R. Taking the proof for this, so z transform of x of n, which is nothing but x of z, is equal to summation n varying from plus infinity to minus infinity z to the power of minus n. Now differentiating on both sides with respect to z. So we will get differentiation of x of z with respect to z is equal to, so this summation will remain n is equal to minus infinity to plus infinity x of n. Now z to the power of minus n, if you differentiate that, you will get minus n z to the power of minus n minus 1. Okay. Now taking this z to the power of minus n and is minus 1 outside, and we have a minus here, so I will take this minus outside and the z inverse outside. So I will remain with n is equal to minus infinity to plus infinity. So I will write n here and here x of n and z to the power of minus n. So this minus I have taken outside. Okay, so that won't change anything here. Now based on this, I can write this as minus z inverse minus z inverse. So this term, if you look at this entire term, if you compare this with equation 1, so in place of x of n, we have n into x of n. So that means I can write this as z transform of n into x of n. Okay, so this term, and here we have differentiation of x of z with respect to z here, and we can write this 1 by z into z transform of n into x of n dx of z by dz. Now if I cross multiply this entire term keeping only z here, so I will get dx of z dz, the differentiation of x of z into minus z is equal to z transform of n into x of n, or I can write it in a proper way, z transform of x of n into x of n is equal to minus z differentiation of x of z. Hence the proof for differentiation. Next property is initial value theorem. So it says if x of n is 0 for n less than 0, then limit n tends to 0 for x of n is equal to x of 0, it is limit z tends to infinity x of z. So the simple way of understanding is, if you apply limit n as n tends to 0 for x of n, then you will get x of 0. That is in time domain. In frequency domain, if you apply limit z tends to infinity for x of z, then also you will get x of 0 only. So that is the meaning of initial value, where x of 0 is the initial value. So that is the initial value theorem. So if we take the proof, so the z transform of x of n, that is x of z is equal to summation n equals minus infinity to plus infinity x of n z to the power of minus n. It says if x of n is 0 for n less than 0, that means x of n is not present for values of n which are less than 0. So that's why we have x of z is present only for values of n varying from 0 to infinity, x of n z to the power of minus n. Okay. Now coming to this term, if you expand this x of z, so what do you get? Apply value from 0 to infinity, x of 0 z to the power of 0 plus x of 1 z inverse plus x of 2 z power minus 2 plus x of 3 z power minus 3, and so on all the way to infinity. Now for this, taking limit on both sides as limit z tends to infinity. So here limit z tends to infinity, x of z is equal to, so what happens to this term? Limit z tends to infinity, so x of 0 plus x of 1 1 by z plus x of 2 1 by z square plus so on. Now if you take this 1 by infinity, that is 0, 1 by infinity square is also 0. So you will get 0 for this term when you apply the limit. So you will remain with x of 0 plus 0 plus 0 plus 0 plus all the way to infinity. So what you will remain with, limit z tends to infinity is equal to x of 0. So that is the proof of it. Z tends to infinity, this limit, if you apply this, you will get 1 by infinity, which is 0. So that is the initial value theorem for this. And to the right, and this one is simple here. It says if you apply limit n tends to 0 for x of n, you will get x of 0. So that is the proof here. So going to the last one, final value theorem. So it says if x of n will give you x of z, and there is a condition, if x of z exists and no poles outside the unit circle and it has no double or higher order poles on the unit circle centered at the origin of z plane, comma, then so limit x of n as n tends to infinity is equal to x of infinity is same as limit z tends to 1 for z minus 1 x of z. Okay. Now coming to the proof for this, so we have z transform of x of n as x of z. So you can call this as equation 1. So z transform of x of n plus 1. So this can be written as z into x of z minus z x of 0. So you might be wondering how we got this. It's just the simplified version I have written. I have not written in detail here. You can apply the time shifting property for z where n is equal to minus 1, and if you expand that you will get this term. Okay. Now subtract equation 1 from equation 2. So what you get, z transform of x of n plus 1 minus z transform of x of n is equal to z into x of z minus z to x of 0 minus x of z. Now we have x of z in common, so you can write it as z minus 1 into x of z minus z x of 0. Now to the left, this is a transform of x of n plus 1, and if you elaborate this, n equals minus infinity to plus infinity. And one more thing, the limit won't be from minus infinity to plus infinity, because x of n is not present for negative values of n based on the initial value theorem. So we can write this n is equal to 0 to infinity x of n plus 1 z to the power of minus n minus summation n is equal to 0 to infinity x of n z to the power of minus n. So we can combine this summation n is equal to 0 to infinity x of n plus 1 minus x of n z to the power of minus n is equal to z minus 1 x of z minus z x of 0. Okay. Now taking limit on both sides as limit z tends to 1. So what do we get? Limit z tends to 1 here, summation n equals 0 to infinity x of n plus 1 minus x of n z to the power of minus n is equal to limit z tends to 1, here z minus 1 into x of z minus z x of 0. Okay. Now, if you observe this, if I put z is equal to 1, so this term, so what happens to this term here is, you will get 1 minus 1, 0, x of z, and this becomes 1 into x of 0. Okay, so this part is fine. So what about this term? So this term, if you see this, z is equal to 1, if you apply this, so this will be 1 to the power of minus n, and this, if you elaborate, if you apply the value from 0 to infinity, so it will take at some point as x of infinity and x of infinity plus 1, and here it will be 1 to the power of minus infinity. So that means you will get infinity itself, x of infinity all the way, and rearranging this, so we'll end up with limit z tends to 1 summation n is equal to 0 to infinity x of n plus 1 minus x of n. So this is whole term z to the power of minus n plus z into x of 0, limit z tends to 1 z minus 1 into x of z. Okay. Now, if you look at the definition, it says, so if you apply limit as n tends to infinity to x of n, you will get x of infinity. It is same, but if you apply z tends to 1 for this term, so you will get x of infinity. How means, you can say this term, if you apply z tends to 1 here, so this term z tends to 1, this will be 1 to the power of minus n plus 1 into x of 0. So this term we have to apply from 0 to infinity, so you will get x of infinity itself. Okay, n takes 0 to infinity, the final value will be x of infinity. So based on that, so we can write, so this limit z tends to 1 z minus 1 into x of z is equal to x of infinity. So that is the proof for final value theorem. Okay. Now we'll take some examples on this. So it will be asked in this way: using appropriate properties of Z transform, comma, or using appropriate properties, find Z transform of. So here I'll take the first example. X of n is equal to 3 into 2 to the power of n u of minus n. Okay. So this is the problem that is given. So if you look at this, we have u of minus n. So that means n is time reversed. So there is a chance that we can apply time reversal property. So what does time reversal says? So this is for reference I am writing. So if you have x of minus n, so the z transform of that will be x of 1 by z. Now if you have x of z, then it will be x of 1 by z if the signal is time reversed. Okay. Now let's find this for x of z first, then we can replace z with 1 by z, we get the answer for that. So if you look at this, we have a derivation alpha n into u of n. So the z transform for this is 1 divided by 1 minus alpha z inverse, where z is greater than alpha. So this is the very first, so these are the standard z transform derivatives that you have to remember while applying the property. Now in place of alpha, if I replace 1 by 2n into u of n, so the z transform of this will be 1 divided by 1 minus 1 by 2 z inverse, where z is greater than 1 by 2. Okay. Now here we don't have u of n, we have u of minus n. And then we can write 1 by 2 to the power of minus n into u of minus n. So for this, the z transform will be 1 divided by 1 minus 1 by 2. Here we have z inverse. Z inverse is there. Since we have minus n, so this z inverse, or you can write z inverse here, and the rest write z is equal to 1 by z. That is what you have to apply. So if I do so, you will get this as 1 divided by 1 minus 1 by 2 z. Okay. Now to get this happen, we have 1 by 2 minus n u of n, but here we have 2 to the power of n into u of n. Rewriting x of n is equal to, I can write this 3 into 1 by 2 to the power of minus n into u of minus n. So this won't change anything because we have 2 to the power of n. So I have written 1 by 2 to the power of minus n, that is nothing but 2 inverse of minus n. So that will be the same. So now we can use this one, this term. So that means we have applied time reversal property, and only this part of the signal is taken. This 3 is not considered here. For that, if you observe this, 3 is a constant, and this entire term is we can consider it as a part of x of n. From linearity property, so it says a x of n plus b y of n. If you perform z transform for that, you will get a x of z plus b y of z here. So therefore, for 3 into 1 by 2 to the power of minus n into u of minus n, so this can be written as 3 into x of z plus 0. Y means we don't have any y of z term, so that's why. Now 3 into what is x of z? If you look at this term, so this is our x of z, which we obtained for 1 by 2 minus n u of minus n after applying time reversal property. And here z, what happens to z? Z will be less than 2 because we have replaced z with 1 by z. That's why. Coming to this term, so 3 into x of z is 3 into 1 divided by y 1 minus 1 by 2 into z here, or we can just write it as 3 divided by 1 minus 1 by 2 z. We can further simplify this to bring it to a much simplest form, or you can just write it as z transform of 3 into 1 by 2 to the power of minus n into u of minus n is equal to 3 divided by 1 minus 1 by 2 z. That is the final answer. And while applying the property, you have to observe the input signal, and to apply the property you need to make some small modifications to the input signal x of n, especially while you are using property to get the Z transform. So here we have to use the property, it is clearly mentioned. We can't use the basic definition of x of z and we keep on going by taking the limit and all. So you have to use the properties only. So while applying the properties, if sometimes it is necessary that we have to make some modifications, so that is allowed, so that the input signal won't change, it will remain the same, but for our convenience to apply the property, we have to make those changes to the input signals. So I'll take one more example for this one. The same thing, using the properties you have to find Z transform given x of n is equal to n square 1 by 2 to the power of n into u of n minus 3. Now I will rearrange this x of n, or I will rewrite this. You observe this, you have u of n minus 3 here, but we have only n here. So that means uh, it will be better if I have the same n minus 3 term here, because I can apply the time shifting property for that. So what I will do, rewriting x of n. So I am just specifying for your reference, you don't need to do that. So 1 by 2 n minus 3, since I am using n minus 3, I should also make this cancel. So I'll multiply with 1 by 2 to the power of 3, okay, into u of n minus 3. So finally I can write it as 1 by 8 into n square into 1 by 2 to the power of n minus 3 u of n minus 3. So this is my x of n. Now you can see this, we have same shifting here, so we can apply the property, same time shifting property. What does it say? From time shifting property. Now I just considering only this part of the input, I am not touching this 1 by 8 n square, okay. So only this part of the input. So 1 by 2, so from time shifting property we have x of n minus n naught is equal to z to the power of minus n naught into x of z. So this is for the reference. Now we have this signal for 1 by 2 to the power of n into u of n. If you apply this Z transform, so what do you get? You will get 1 divided by 1 minus 1 by 2 Z inverse, where Z is greater than 1 by 2. So as in the previous problem, I am starting here. Now if I apply time shift for that, so 1 by 2 to the power of n minus 3 into u of n minus 3. So this is the time shifting property. So that means I have to use the time shift here. So z to the power of minus n naught is there, that is z to the power of minus 3, okay, into x of z. So this is the x of z into 1 divided by 1 minus 1 by 2 z inverse. So this is the time shifting property I have written. Now we can simplify this. That will give you z to the power of minus 3 divided by 1 minus 1 by 2 z inverse. So if you observe, I have taken only this part of the signal. Remaining 1 by 8 n square is there, so that I have to consider. If you observe, we have differentiation property, which is z transform of n into x of n. I'll write this from differentiation property. So from the differentiation property, so we have z transform of n into x of n is equal to differentiation minus z into differentiation of x of z with respect to z. Now this x of z is this value only because this is the part of input as well. So that's why. Now we have n into x of n. To make that happen, I will rewriting x of n as x of n is equal to, I'll write 1 by 8 n into n 1 by 2 to the power of n minus 3 u of n minus 3. Now this part of the signal we have found, I have just split that n square into n so that I can apply in this form. So therefore I'll take this part of the signal z transform of n to 1 by 2 to the power of n minus 3 into u of n minus 3. So as you can see, this is a part of input, so n into x of n. So that should give us minus z differentiation of x of z is z power minus 3 1 by 1 minus 2 z inverse. So this is differentiated with respect to z here. Okay. So the differentiation of that will be minus z cube is there. So you should get 3 z square minus, I think 2 by 2 will get z here divided by z cube minus 1 by 2 z square whole square because I can write this 1 by z square z cube. Now if you simplify this, I think you should get this term 3z cube minus z square divided by z cube minus 1 by 2 z square whole square. Okay, so this is the z transform of n into 1 by 2 n minus 3 u of n minus 3. Now again using differentiation property. Now this term is the new x of z. Now the z transform of n into 1 by 2 to the power of n minus 3 u of n minus 3. So that should be minus z differentiation of 3z cube minus z square divided by z cube minus 1 by 2 z square whole square. So this is with respect to z we have to do. So this entire term we have the x of z for this. Now I have taken this n into x of n. So again differentiation property I have applied. Now minus z into, if you differentiate this once again, that is 3z cube minus z square divided by z cube minus 1 by 2 z square. I think it's a little bit lengthier. This is what you are supposed to get. Let those 3 z cube minus z square into 2 into 3z square minus 1 by 2 minus 9z square minus 2z into z cube minus 1 by 2 z square divided by z cube minus 1 by 2 z square. This becomes, I think, whole cube. Z term will be cancelled. Now if you keep simplifying this, you are supposed to get something like this: 9z to the power of 6 minus 21 by 4 z to the power of 5 plus z to the power of 4 divided by z cube minus 1 by 2 z square whole cube. So this is the x of z value. And finally, using linearity property, so a x of n plus b y of n should give a x of z plus b y of z. The same way, z transform of 1 by 8 into n to 1 by 2 n minus 3 u of n minus 3. So this should give 1 by 8 into x of z plus 0. Now this is 1 by 8 and the x of z value is 9 z to the power of 6 minus 21 by 4 z to the power of 5 plus z to the power of 4 divided by z cube minus 1 by 2 z square whole cube. So to get the end value, you have to, the simplification part is important to reach here, so that you have to, it's just multiplying and simplifying the remaining part. Sub terms will be cancelled here. Now that is the important part you have to deal with. So this is the final answer you should get for this one. And remember, we have to use the properties, only the properties, to get the end result for this. So that's why. And I will give you a one more problem. You just try this at home on your own. N sine pi by 2 n into u of minus n. So here if you observe u of minus n is there, so that means you have to apply time reversal property, and this is in the form of n into x of n form. So again differentiation property you have to use. This sine pi by 2 n, you have to convert that into exponential, then you can apply the remaining part. So that step is important here. Take one signal at a time. So first take this term, and afterwards you can first apply this n into x of n first, and then you go with the time reversal property, or you can rearrange this like x of n is equal to minus n sine minus pi by 2 n into u of minus n. So this also you can do for this, and you can apply the properties, differentiation and time reversal. Okay, while applying time reversal, you can rewrite this into this form. So finally you should get x of z for this as a z cube minus z divided by z square plus 1 whole square, where z will take 1 by z here. So this is the final answer, or if you apply that z is equal to 1 by z, you should get z into 1 by z square divided by z square plus 1 whole square. So final answer. If you are not applied z is equal to 1 by 2, at least you have to mention this, but to get the final result you have to apply the value for z. So try this on your own and check whether you will get this as end result. You have to apply those two properties for this problem. Okay. In the next, I will take some examples on this only, and I will move to different kind of examples in the next video. So if you have any queries, do comment on this video or do reply. Thank you for your time.